I wanted to give an update on the state of the hardware for the DMX handheld console project, and also talk a little more in depth in regards to what the code actually looks like, because aside from actually testing it, the code is mostly complete at this point. And so I have components on the way to me to build a baseboard, and this is, or a control board, and this is the layout for the control board. It includes the PIC32, it includes some power circuitry. I'm able to take a 9-volt battery or a USB connection into the device to power it, and I've got the microcontroller, I've got a header for the user interface board here, programming header, and the DMX control, which is using an isolated circuit here, and I've got the DMX transceiver here, and this header that I can just use to connect to an off-board DMX connector. And so this is the new version of the user interface board. I did fix the issue I talked about in the last video, and also made a couple other improvements from having played around with the current version of the board. And so once I get the components for this guy here and I verify that all the footprints that I had to do manually are correct, then I'll go ahead and order these PCBs and start building the hardware for the project and see how it looks. So now talking a little more in depth in the code, and again, this might go a little long, so if this is not going to be interesting for you, you might just want to skip this part. But I've started off by splitting up the Harmony library here, or the Harmony functions here, and I've got them on separate groups, and show them over here in this tab. So for my command line interface, I've added a timer, and this timer is going to enable us to do the fading that we talked about, and we'll hopefully go a little bit into how I managed to do the fading, because it took a little bit of effort to figure out exactly what I wanted to do, try to avoid using floating point math, and just try to get it accurate with as little CPU overhead as I could. For our DMX port 1, we've just got our timer that's controlling the break and the mark after break, and then the UART that is actually sending the data. DMX port 2, I've completely commented out all of the port 2 and receive related code, and so I just mark this as unused. I have it there in case I decide I wanted to add a function later, but this is marked as unused. And then for the user interface, one of the big things in the hardware here with this board, transitioning from the microelectronica clickboards, is that the OLED is now using the SPI interface, or the SPI, as well as the keypad. They're both using the same SPI port. And so what I've done in the code is I've actually combined the SPI handlers into one specific thing that's able to split out and figure out whether a transaction occurred that was originated from the keypad or from the OLED, and I'll talk a little more about that when we get to the code. Then we've also got our timer here that just generates the 5 millisecond delay for the keypad, so that we're not pushing data, we're not pulling data from it too quickly. It just gives us a little more time. It makes our debounce code a little bit easier. So in terms of the actual code files, I've added, again, like I said, a couple new things. Most of this is the same. However, I replaced the OLED and keypad inits with this UI init. And this UI file is where, as I talked about, I'm splitting out the handling of the SPI functions. And so what happens is I have this set active device. Whenever I'll go to the keypad code here, and let's see if I can find it. So whenever we go to do an SPI read, and I did not make the update here just yet, so we'll go to the OLED, and I'll have to fix that keypad code, but over here in the OLED, we're just going to sit around in this while loop waiting until we're able to send data over the SPI, and hopefully I'll be able to optimize this out and maybe do some sort of buffer or a queue for that data, but right now I just have this while. So we're just waiting to see if we can set our active device for the SPI port to the OLED, and that's just defined if no device is active. So if all of our SPI transactions have completed, then we're able to set our active device. Otherwise, if there's a transaction in progress, then we return false, and this will just continue waiting. And so that function right there is what allows us to actually split out this handling, because once we've done that, that means we're good. We can start our SPI transaction. So we'll set or clear our data command bit here, and we'll clear our chip select just to make sure that both of these are active or inactive, whatever we need. And then we'll do our SPI write here. And once the SPI calls back using this callback here, we'll look at our currently active device, and if it's the keypad, we'll jump into the keypad file and we'll run its callback handler. If it is the OLED display, we'll jump to the OLED file and run its callback handler, and then we'll just set back to device none to tell the system that we're ready to go ahead and move on and run our next function here. So as I talked about with the OLED display here, we've moved to using SPI instead of I2C, and it was a pretty simple transition. I actually added in one extra function here that allows us to write an array of data. And the reason I'm able to do this a little more easily here is because with the I2C, I would have to write a byte, either 0x00 or 0x40, depending on whether we're sending a command or data, and then start sending data. And I didn't really want to have to deal with playing with pointers and trying to figure out how to get that one byte to send and then get everything else to send, or sending them in separate transactions. And I just didn't deal with that with the I2C. It wasn't worth the effort because I knew I was going to be transitioning to SPI. It was just easier with the I2C to do the prototyping. And so I've added this data array write, and the main change that we're making in terms of how we're sending our data is, like I said, I have to send that 0x00, 0x40, depending on whether we're doing data or command. In this case, I'm just setting or clearing a pin. That's all I got to do. In addition, I have to make sure my chip select is pulled low, so that way the OLED display knows that we're talking to it, and then we can start sending data. And that was really the only changes I had to make. Since I had this data array write, I went ahead and went into the update screen function here, and originally it was sending 128 different I2C transactions for each page or each row, each set of 8 rows. But in this case, since I've got this data array write, I can just dump the entire page out in a single transaction, increment the page. Makes things a little bit simpler in terms of what the code has to do, and cuts down significantly on the amount of data that we have to send. And another change that I had to make that I knew I was going to have to make, but I kind of feared it. I thought it was going to be more complicated than it really was, but it turned out to be incredibly simple, was handling the extra 8 buttons in the keypad. Really, all I had to do was increase this raw keypad data. Since I only had 16 bits before, I had a 16-bit unsigned integer. Now it's a 32-bit because we've got the 24 buttons for 24 bits. We're only sending 3 8-bit bytes. And then in the callback, what I actually did was I had where in the heck is it? Oh, down here, sorry, in the process button press, I had this massive switch statement that would say, if the activated button is button 0 through 2, we would add 1 to that value and then run our CLI add to command with whatever that value was. And in this case, what I actually did was I just created an array, a keypad mapping array. So up here where it's defined, here it is, button 0 is going to be this 8, button 1 is 5, button 2 is 2, button 3 is 0, etc. So literally what we're doing is whatever button is active, 0 through 23, we just grab whatever that function is out of this array, and that's what we're going to send to our CLI add to command here. And that definitely cut down on the lines of code significantly, and as opposed to having a switch statement with 16 different cases, each one of them has to have the CLI add to command and a break, and so that was a lot of extra lines of code. The other change that I made here was I increased my counts in my for loops to 24 just to handle the extra 8 buttons, and I realized this is still set to 16 in my initialization, so I got to fix that. And other than that, there's not really much that changed in here. I do still have to fix the callback here, so I'll be right back. Alright, that was an easy fix. All I had to do was add this while not set active device for the keypad, and then we're just going to sit around and wait until I'm able to actually send data using the keypad. So my last transaction is complete. We can go ahead and send data with the keypad and run this. Again, not the most ideal way to do this. I hopefully will get this fixed at some point, but we'll see. So the other change, like I said, with the DMX file, I just went ahead and commented out all of the port 2 stuff, so that way we're not taking up any extra space here. And that was a pretty easy change. I already had the UART2 disabled, all the port 2 disabled, all the port 2 stuff disabled. It wasn't actually doing anything, so literally just commenting this out changed absolutely nothing. The program built just fine first try, so that was great. The other main thing that I did is in the CLI file, and this file is a dauntingly, I'm 4 lines short of 1,000 lines here. This right here, this process command, is an absolutely massive beast, and I honestly can't tell a better way to do this. This method that I'm doing has actually been working perfectly fine, and I'm sticking with it at least for now. But this file is kind of how I handle all of the actual command line processing. And so what it does, let me pull up my Excel spreadsheet here. This actually got so complicated that I created this spreadsheet, and you can see what we have on the left side here is all the states. So the program runs in a series of states, a finite number of states. And so what'll happen is we'll start with a command section new. It'll break the command into multiple command sections. So if I were to do something like, say, 1 at 50 plus 2 at 35, that would be 2 sections, 1 at 50, and the second section would be 2 at 35. And so we start off with a new section, and when we're in this section, we're going to look at what the next command is, or what command we need to process now. And this table here is just telling me when I'm in a specific state which commands are valid. And that was a huge help for figuring out how I was actually going to handle all of these commands. And so what happens is start off in section new, and then I can hit, say, record or preset or one of these, and I'll move into, sometimes I'll process some data, but every single time I will move into a new state. And this table down here, it's not entirely accurate, but this does a pretty good job of telling me when I'm in a specific, or which buttons will take me into a specific state. And so that just helps me know what these two tables just help me know how my program is flowing. And it definitely made that massive chunk of code here a lot easier to actually program, because I at least had an idea of how the flow was going to work. And that's a major thing that I like to do with this, is that I will have Excel spreadsheets that will just kind of tell me what's going on with my program. This right here is actually my spreadsheet that gave me my keypad mapping. So over here, you can see I've got all my buttons, and if I bring up this right here, these numbers are which shift register I'm dealing with, and then the letter is what input on the shift register. So you can see the top left here is register 1, it's going to be input H, and then register 1G, we go all the way down to E, and then back up, and then down and back up, down and back up, and it was wired this way just to make things easier on the actual routing side. And so I've got that reflected here. I've got how I want to assign all my buttons here, and then based on these and based on what I know about how the PIC32 is actually going to pull in the data from the 74HC165s, I was able to figure out my mapping here. Buttons 0 through 23 is each of these. And so, like I was saying with this sheet, this was a massive help for figuring out the flow of this program here, because there's a lot going on in this, and I could not nearly talk about the massive amount of stuff that's happening. But I do want to point out one thing. So this sheet right here is a fade algorithm test, and this is kind of how I figured out what algorithm I was going to use for fading values in and out. And so what I've actually done is I'm using this one right here. This is a slightly different one that I wasn't a huge fan of, but this one right here is what I'm going for. And these are some test values here for what the initial is, which is what our unit is currently sending out, and our goal, which is what we've calculated is the endpoint for the fade. And so what's happening is we're going to, first of all, calculate a coefficient. And this is the number of value. This is the amount that we're going to increment every time we hit a certain number of ticks. And that number of ticks, you can see our timer is running 7.8125 milliseconds, which is 128 ticks per second. This is the timer 3 that we talked about in the Harmony library here. And so what happens is every 3 ticks, because we're going to be dividing this by 128, and I'll explain why in just a second. Every 3 ticks, we're going to add 255 to our tracker value. And these guys right here are actually a modified value for our initial and our goal. And all we've done here is just multiplied the initial and goal here by the number of ticks per second. And so this is a terrible way to explain it, but hopefully it'll make sense, and maybe I'll go back to the code and try to explain this again. But what's going to happen is we start off with a value of 0 in this case. Every 3 ticks, every 3 128ths of a second, we're going to add 255 to it. And what's going to happen is we're going to take that value, that's going to be our tracking value, we're going to take that 255 and we're going to right shift it by 8 bits. And what that is actually going to do, or in this case, sorry, it's actually going to be 7 bits. I'm going to have to fix that in the code. We're going to right shift it by 7 bits. And what that's going to do is since 128 is 7 bits, when we right shift it by those 7 bits, we're actually going to lop off the ending value of this. And what that's going to allow us to do is it's actually going to wrangle this value back into our range of 0 to 255. And again, this is a terrible way to explain this. Let's just go to the code and I'll try this again. So first of all, like I said, I need to drop this down to 7 bits to deal with our new value here. So up here, when we complete our command, when the whole thing has been completed, we've hit the enter key or the full key, we're going to check and see if we're in set values, if we're trying to run a preset, if we're recording a preset, whatever. If our fade time has been set, so we have a fade time, what we're going to do is we're going to start by setting up this fade tracker. And all we're going to do is take the current value for each channel. We're going to take the current value that we're sending out, multiply it by, in this case, 128. So now what happens is, if I take this value and I right shift it by 7 bits, we're going to get the value that we're currently sending out. So for each of our active channels, if the channel is inactive, we're going to set our fade coefficient to 0. Every time our timer ticks back, we're going to do nothing to that channel. Otherwise, we're going to set up our fade coefficient. All we're going to do is set the goal minus the initial value, and that's going to be how many numeric values we're going to increment or decrement if it becomes a negative number. This is a signed integer, by the way. That's how much we're going to increment or decrement every time our timer hits those that certain number of ticks. That is based on how many seconds we have. And so if we go down here, so let's use the example. Let's see if I can split this. There we go. So for our example here of 0 to 255, we're going to get rid of that, and we'll get rid of that. Give ourselves some more space here. There we go. So what's going to happen is the fade tracker here is going to be set to our current value times 128. In this case, it's 0 times 128. So our tracker is starting off at 0. And our coefficient is going to be the ending value minus the initial value. In this case, it's going to be 255 here because our goal is 255. And scrolling back down here, what's going to happen is every time that timer calls back, we're going to increment our wait tracker. And this is just counting how many ticks that we've gotten, how many times the timer has called back since we started this fade. And so we're going to check and see if that tracker is equal to, if that tracker mod our number of ticks, in this case it's going to be 3. We get that value from the number of seconds that we need. So if that's going to be 0, that means that the timer is ticked over 3 times. And so now what we can do is we're going to increase our tracker value by our fade coefficient. And you'll remember that 255 here, if I bring up a calculator, 255 times 128 is going to be 32,640, and you'll notice that's our goal here. So what happens is, since we've got 128 ticks per second, we're running, in this case, 3 seconds is our example time, so we've got a total of 384 ticks. That means that every 3 ticks, we need to increment our value by 1/128th of the goal. And in that case, it's going to be 255 is 1/128th of our goal here. And so after those 3 ticks have occurred, we can increment this by 255, And then what we're going to do is we're going to adjust our output value to be whatever our tracker is, but we're going to right shift it 7 bits to deal with that 128 that we've incremented. Since we're multiplying our goal here, or our actual value, by 128, if we right shift it 7 bits, we don't have to divide anything. We just right shift it. It's an easy operation for the microcontroller to do, and we get our output value. And this will, as is shown here, actually give us a dead accurate version of what our output wants to be. So we will get, if we take this and we divide it by our number of ticks per second here, you can see that we will get a whole number representation that is exactly equal to what our goal is here. So this is a precise way of doing this. And it's a really easy way to do this. We're not doing any division. We're just doing this right shift operation. We're doing some addition and okay, we are doing this modulus function here, but we're only doing it once for the 512 channels. So I'm gonna take that excuse and run with it. And then what happens is, once we've reached the total number of ticks that were supposed to happen, which is, in the example time, it's 3 seconds here, is our fade weight ticks times 128. Once we've reached that total number of ticks, we go ahead and stop the timer. We're also stopping the timer every time the command is completed here. So if I type another command and hit enter, we will actually override the fade. The fade will stop exactly where it is, and we'll just stop right there, stop the timer, and we'll override it with something new. And of course, down here, when we're running our fade, we got to start the timer. So as I mentioned at the beginning of this video, the actual code itself is not tested. All the additions that I've made, all the changes that I've put in here have not actually been checked yet, so I'm not guaranteed that it's all going to work. Something could change. I am keeping my GitHub page updated, and this is actually a good time to plug my GitHub page here. You can see I'm at K McNichol, and this whole project is uploaded to GitHub through MPLab. I'm not super familiar with using MPLab in terms of the actual using the actual Git functions, so hopefully I get everything running correctly. Hopefully the code is usable, and if you have any questions, definitely feel free to reach out to me. Feel free to check out the GitHub, check out the code, play around with it, see what you can do. And I hope you found this video helpful. If you stuck around for the entire about 30 minutes now, I really appreciate it. And thanks for watching.